then how it is to get better, right? So that's the actual learning process. So by me correcting homework, I'm doing the learning process and you guys are skipping. So I will give you homework credit for essential effort, but if you guys want to do learning and figure out where you got things right and wrong, you've got to go back and look at the solutions and pound through everything yourself. All right? Everybody get it? It's not me. This is the way I think. All right? And I think this way because it's better for me, of course, but I think this is truly how you learn. So I think you learn by batch processing things in your head over long periods of time and looking at it many, many times, not just once. And if I'm grading homework, I'm the one that's looking over it many, many times and thinking about how things went right and wrong. So you've missed that opportunity. You know, if I show you how to do it right, you haven't considered how you did it wrong and why you did it wrong and how next time you wouldn't go down that way. All you know is the right answer this time. Anybody buying this philosophy a little bit? Okay. Okay, those guys get A's. All right. So that's my philosophy. You can buy it or not, but that's what we'll do. So lectures, I'll never take attendance, all right? But I'll never know what the homework is. So if you miss a class, I'll have no idea what the homework was. That's your job, all right? And I'll never know when tests are. I'll say when they are in class, but after class, I'll never know when the homework's are due. I'll never know when the homework problems are. I'll never know when the tests are. All right? Everybody got it? So if you miss class, it's up to you to figure out how to do it. Unless you're sick or something, then you can talk to me and we'll figure it out, right? And then homework, you got to try it. So I really think the learning here is homework. All right? Again, I'm only saying you should be insulted that I ask you to get homework back. Right? Homework is very key, and what it is what homework is really putting in effort. And here's the thing for disaster is throwing something together for homework the night before it's due. All right, that will never work. All right, and you'll run into trouble. Here's the best way to do it: is try a little bit of each homework problem every single night. Even if it's just reading the problems the first night, then it's sitting in your head. Right? And in your head, you're kind of going around things and like, how should I start? And so if you just read the homework problems and draw a picture on the first day, then that thing is in your head, and then maybe the second day you write down something, and then maybe the third day something comes out wrong, but then you've got a good question to ask me. So you email me, and then you go, okay, now I get it, and then it's ready by the next week. And so that's the process that I want to see. Okay? Everybody's heard this right before, but I feel like I have to say it. All right. Yeah. Key to success is effort. Use Maple and Excel and LabVIEW. All right, because they make us better mathematicians. All right, but here's how to get into trouble. Typical computer speak is garbage in equals garbage out. So if you use a mathematical symbolic program like Maple or Mathematica, that if you don't know what you're doing and you put something in, it will give you an answer, but it will be crap. All right? So you've got to know what you're doing to make these programs powerful. All right? And then I wanted to, just while we're on that note, Dale Smith brought my attention to a free computer algebra program. And so I've got you guys on Blackboard, so everybody should check out Blackboard. And on Blackboard, I put a link to it, and it's called Maxima. And it's fantastic. All right, and what's nice, it's a freeware stuff. I think it's by people at MIT and stuff like that, and it's just held together by pure mathematicians. And it has all the look and feel and everything of Maple, but in Mathematica. But you're not forever, trying to keep up with the upgrades and stuff like that. So if you go to Blackboard and there's a link there, it'll show you how to download them, and it's great. It's really nice. All right. They have great, you kind of go by some of the examples and then you'll get up to speed with how to do it. Right? All right, if you do go to Blackboard, let's see, there's a bunch of things that I had there, and I'll add more things. If you find interesting things like on a given topic, I'll put them in here. But here's it, in there I've got like articles for quantum, and one of the homework, that you've got to do before next Tuesday is read the AJP Max Born article. So you've got to go to the Blackboard account, you've got to get that AJP article. I don't care if you print it or just read it off the web, but it's the Max Born article. It's AJP 73 Max Born Bernstein.pdf. Okay, so that'll be an article there that you've got to read. You know, I have a couple other links and notes and software and things like that. Right? So I'll post things on Blackboard that you think are interesting and that I think are interesting, and that would be cool. Right? Alright, so that's not bad. Alright, I'll tell you super quickly about me, no longer a big deal. So I finished my PhD in 1993 from the University of Connecticut. I actually went to college at UConn. And the scoop was that I wanted to be a physicist, but my guidance counselor didn't know what physics was, so he thought I should be an engineer. And the truth of the matter is I wanted to play tennis. So I said, okay, I'm only going to school to play tennis anyway. So I went there and I played tennis, and I was a mechanical engineer, and I graduated in 4 years. And then when I got all done, I went to work. And work was very unfulfilling for me. I took graduate courses in engineering. It was very unfulfilling for me. So what I really wanted to do was get back into physics, because that's what I really liked. So nobody would let me in because I was not a physics undergrad. So what I did is I got physics books and I did them on my own. Alright? That's the whole point of being a physicist, is get good books. Do the work on your own. Alright? You can do it. And what happened is at UConn they said, look, you can't get in, but we'll let you take math methods for physics. It's the graduate course. And so I took that for a year while I was an engineer, and I did very well in it. And then at the end of the semester, the professor said, you know, Ed, what's your deal? I don't see you around the graduate school. And I told him what was going on, and he couldn't believe that I was doing that. And he said, if you want to get into graduate school, I'll help you, because you can do math. All right? And so what happened is he went and talked to the graduate school, and then they let me into the PhD program based on my ability to do math. All right? And then what I did is I did like mechanics on my own, and I did E&M on my own. But when I got in the graduate program, I did undergraduate quantum and then undergraduate E&M again, all right, just to get everything that I needed. And then I went and I took all the graduate courses. And so then I finished my PhD in 93. I had a bunch of postdoc offers from a lot of different places when other people didn't have any. All right, and I decided to go to Oak Ridge National Lab in Oak Ridge, Tennessee. My advisor there, it was the 2000 United States Fermi Award winner. That's the highest medal of science given by the United States. All right, so his name was Sheldon Dax, a great guy. He died only a year or two after that, but he was incredible. You know, I smashed atoms, kind of looking at electron and molecular orbitals. There was a lot of atomic physics. But with Sheldon had a great idea, and we went and did that idea at CERN in Switzerland. All right, so we looked at this process, which was trying to break quantum electrodynamics to try to see where it fails, because that's when you get smart. When your theories fail is when you get smart. But anyway, the bummer is that the theories worked perfectly well. What we were looking at is multiple electron pair production from the vacuum. All right, quantum electrodynamics predicts this, and we got those numbers. So it was at CERN. We did the experiment. It took a year at Oak Ridge to make it. And then we shipped over to CERN 28 cartons that were like this. They were like 8 by 8 by 8s in a separate plane. The plane went over there to Europe, dumped it over at CERN. We got over there to CERN. It was only 6 people from 4 different countries in my group. We got there, we put it all together, got the beam, did our experiments. Took about a month, and then we came home. So it was very cool. All right. And then after that, I came back to the States and decided to live in this area. So then I took a visiting position at Lec1 College. So what happened is my wife is a veterinarian, so we said Tufts for her. And so I said there's a lot of colleges, so I'll take a college job. Even though I had done a postdoc and everything, I was looking more for a university job, but that's okay. This offered me a lot of flexibility. And so I took a visiting job at Lec1 College. And it's just down the road in Norton. And after that, I took a visiting job at Amherst College in Amherst, Mass, which is this year was rated the #2 college in the country. So when they rate colleges and universities, there's two categories. There's universities and there's colleges. And this is pertinent to us because we just became a university. So if you go to a place like Wheaton College or Amherst College, those are true colleges. In other words, they don't support any graduate programs at all. So there's nothing there for graduate students. Everything is about undergraduate education. And then universities support undergraduate and graduate educations. Right? So we've always been Bridgewater State College, but we've always had a graduate program in some fields. Right? And it gets dicey and everything because it's not like you have to have a graduate program in every program. You just have to have so many. Right? And so Bridgewater truly had a number of graduate programs, right, so that we could call ourselves a university. So we're a university in name, but effectively, like in physics, we're still a college, right, which is great because you can do studies to show that the people in the best graduate schools around the country come from colleges, not universities. And part of the reason why is at college is you get really good experience and you get close relationships with the faculty and you can do research. Whereas if you're at a university, most of the faculty are tied up with the graduate students and spend most of their effort in graduate. Of course, that's not a hard rule. That's just a very ballpark idea of what's going on. Because there are great universities where undergraduates can get involved too. So that's what happened. So I was at Amherst. Amherst was number 2 in the country. So they're just well known for their physics department. But when the chance came for me to be here, I took it for a lot of good reasons. All right, and I'm very happy to be here. And I also continued to do experiments at Yale with my friend who we met. Did experiments at Amherst College and at Berkeley. So we did those experiments together. And it was on the fundamental properties of photons. Very good. And then we continue to do experiments. He's the PI at Yale, and we're looking at quark-quark interactions and exchange of these things called Zeeman bosons. But now with the new building and how far the lab's gotten here, I'm going to be concentrating more of my time here. Okay? So that's the big scoop there. All right. And you should know that. I think you should know that of every professor, every course. I think not for any reason except for you to know where that person's coming from. All right? I think it's important to base that. It doesn't mean I'm right about anything, right? But you just know where I'm coming from, and that's it. Okay, so that's the whole introduction, I think. All right. Okay, so we'll start the course. All right. Before I start the course, here's something that's bugging me. This is the start of the course, actually. I contradicted myself. All right. What is the scientific method, guys? Go ahead.
Ask your question.
Yeah.
Do some background research.
Yeah.
Then after you do some background research, you formulate a hypothesis.
Yeah.
Then the hypothesis has to go through a testing period.
Yeah.
As you're completing the testing period, you collect the data and then analyze the data.
Yeah.
And then you come to a conclusion. And then based upon that conclusion, it either verifies or shows that the hypothesis is wrong, in which case you either have to go back and see how you can push the whole experiment to see if you can break it.
Okay, yeah, like I was talking about.
Or if if it's right and it's wrong, you got to see like, well, why is it wrong? And it's not wrong.
Yeah, good. All right, I'm gonna say exactly what Mike said, but I'm gonna draw a picture. Right, and I think this little picture works better, just because you don't get lost in a lot of words and things like that, right? But here's look at nature. Look at nature, and then come up with a theory. All right, and then you have to do an experiment, and then here's our test, and then here's what Mike was alluding to. If the test does not equal the theory, or let's do it this way, if the theory doesn't equal the test, then what does that tell you about your theory?